Hi there, my name is Clinton Jones, and today I want to share with you my research on additive digital fabrication, creating controlled chaos, and 3D printing. Just kind of the topics I'm going to go over today. So first off, before we get into the hard stuff, I just want to talk about 3D printing and why people use it and designers use it. And then, a traditional process from beginning to end that, designers would do. So first, why even use 3D printing? It's a speedy, accurate, and cost-effective way to create models quickly, um, and obviously with little money, whereas, hand modeling can take a lot of money for all the materials. And obviously, like that's time that you could be spending on other things. Where if you use 3D printing, it's machine operated, and you can let it go for 12 hours and then come back when it's finished. And especially with super complex forms that designers come up with, it's an easy way to get those modeled. A lot easier than it would be to hand model it. And it allows a designer to move through design cycles a lot quicker and more efficient. Again, you can get things done a lot quicker and have a quicker turnover time between um, your design iterations. So the traditional process you can kind of see in the 7 steps of the to the side here. First, you create your 3D model in whatever software you want. Traditionally, I use Rhino, but any 3D modeling software works just fine. And then you take that CAD model and you convert it to an STL file. This is the file type that most of the systems you like to convert to. So whatever 3D printer you're using will normally have a custom software with it that will slice it up, and you know it won't make tweaks to your design, but it can add things like infill to help stabilize the project. And with it, you can also specify things to make the 3D printing process go faster or slower. So then, once you get all your settings done in your selected software, um, then you save that file type now as .gcode. So it goes from an SCL to .gcode, and the G code is just a series of numbers and letters that will eventually tell the machine what you want it to do, without writing like it's a numerical way of writing things out. So then once you get your machine all set up and running, obviously it's pretty easy. You just click go, and then the printer deciphers your G code and begins building your desired model. Um, this can take minutes, this can take hours, but again, it's something that you've invested little time into, and you can begin to do other things, maybe even, already begin the next iteration before this one's even done. And then once you're done, there's a little bit of post-production that has to happen. So you have to take your new model off the bed of the 3D printer. And then normally there's excess stabilizing filler that you're going to have to remove. And sometimes to get your model looking super pristine, you might lightly sand it. Just whatever kind of finish you want on it. That's up to you. So then, just kind of what goes into G-code. Breaking that down even farther, because this is what we're going to go into later. So the G-code tells a lot of things, and it's things that you can actually manipulate if you know what you're doing. So as you can see here on the right, there's a model, and the yellow was the original 3D model from whatever software that this person used, and then the red is actually filler that the slicing software is using for the 3D printer to actually add in filler and stabilizer to the model to make sure, hopefully this makes the print successful. But while you're setting up when your STL file is uploaded into the slicing software, you can change certain things. Mainly that's just the slice thickness. And this helps, the process go a little bit faster or slower depending on what desired outcome you're looking for. So the overall geometry is broken down into slices that can be printed one on top of the other, thus the additive nature of 3D printing and this manufacturing process. The slices can vary in thickness. Thinner slices give off a higher resolution, which translates into a smoother appearance. But because you're adding more and more material and taking more and more steps, it's going to take a long time, a longer time to print. And this controls your Z points in the G code coming up later. So talking about the point coordinates, each slice is divided up into a certain number of points. And again, the points will give you differing results in your final product. So the more points for your model that your model gets broken up into, the more points means it's going to be a higher resolution, but again, it's going to take longer because you're adding more and more steps. Whereas if you use less points, you're going to get a lower resolution, so it's going to be a little less crisp, but it'll, the design iteration will go a little bit faster. So it's a lot of, personal preference of what you want out of the model, to justify these settings. So then material extrusion. The machine likes to make things easy, so it wants to extrude the same amount of material each time. But if you actually go in and tamper with the G-code, you can actually change this, and which obviously will change, the outcome of what you're modeling. Again, speed, slower, takes a little bit more time, but can get you a better quality finish at the end. Whereas quicker, you're going to get that lower resolution, but again, you're going to get done in less time, so you get the turnovers a lot quicker. And then what we're going into next, when we talk even deeper about the G-code, is there's a beginning and ending sequence before these coordinates happen. And that tells the machine, your 3D printer, things like, warm up the extruder or warm up the bed, and then, move the extruder to home so it knows exactly where it's at and knows where to begin printing. And then, extra things like the fan, it tells it to turn it on and off. So a lot of what we're going to get into later, but I want to go over it now, is common 3D printing, common commands with the G-code for 3D printing. So common commands that you want to add before you actually print your model, things like G28, it moves your X, Y, and Z in extruder all the way back to 0, 0, 0. This is just something you want to do to let the machine know that it's home and that it starts correctly when you actually begin to print. So then a command like M106S255 sets the fan to full speed. Obviously, very much needed in this because things get super hot and you don't want your machine to overheat. A command like M104S190 and T0 tells your extruder to actually begin heating to 190 degrees Celsius. And everything is in the metric system for this. But your extruder needs to heat up to be able to melt the plastic for when it begins building. And this is probably the longest thing that's going to happen in your beginning process, so this can take several minutes. And then after that's done, then you want to warm up the bed, and that again is the M140 S50 sequence. And then finally, just for good measure, I always tell my machine to home again, just so it knows for sure, and I know for sure that it's going to start from 000. So then, looking at, this will be the main chunk of your G code, is the G1, and this is mainly telling your machine that it's going to be doing a lot of movements. And then it'll be followed by X, Y, and Z coordinates, and those are telling it again an X, Y, and Z axis, so left, right, up, down, back and forth. It's going to tell the extruder exactly where to go to be able to print material. Then you'll see an E and F, and E is telling the extruder how much filament. If you're using plastic, it's going to say how much filament that the extruder needs to release between 2 points. And then the F tells the machine how fast to go between points. And then finally, just some commands for the end is the M106 S0, which turns your fan off. And then when you turn your machine completely off, it'll cool off the bed and the extruder. So just kind of reiterating, the G, insert number, just tells the machine that it's going to be a movement sequence. M, insert whatever number, means that it's going to be a startup or shutdown sequence. X, Y, and Z are all measured in millimeters, and there's just, again, it's a coordinate system of points telling the machine where to go. It doesn't follow paths, it just connects point to point, so it's going to take the path of least resistance from point to point. E and a certain number, again, is going to tell your machine how much material to extrude as it moves from point to point. And then F is going to tell the machine how fast to travel in between point to point. And that's measured in millimeters per minute. Also, again, just some useful tips to remember when you're working on your 3D model is to have your units in millimeter, especially for length and distance, because that way when you get to your STL file and or your Gcode file, you're in the correct units, because if not, things will mess up very easily. And then also you can see in the example commands that I gave, like the G1, X30, Y20, Z1, E10, F1800, you see that I have that in bold, and then there's a semicolon, and then I have text. Well, actually, when you're writing Gcode, anything that appears after that semicolon will not be read by the Gcode, but for you, it might be helpful to know exactly, it tells you what the machine's going to do, but it means nothing to the machine. So you can use that semicolon to add in extra information if you want. That's completely a personal preference of yours. Alright, so now I'm going to show you in Rhino, which is my preferred way of working in 3D modeling, is, how to begin to hack your own G-code to get cool and interesting shapes. So what I have here is just a simple cube. Nothing major, but in Grasshopper, I just want to show you, you begin by setting this as your B-rep. So you want to start by setting that as your B-rep, because that is, what we eventually want to make into a series of points to format into a G-code later. So then the next step is to take whatever shape you have. Again, I'm just doing this in cube, but you want to take that and you want to contour it. This contour is going to be a series of lines in the z-axis that cut your shape, which if I zoom in, you can see that all these lines have been cut into my cube here. And to do that efficiently, you want to set up a series. So this is kind of a step back, but when you get to this contour, you start with a B rep and then a series. So the series has a start, step, and count. So for your start, you always want to start at 0, 0, 0 if you're building a whole thing, unless if you want to do something different, which we'll talk about later. Well, actually, we can talk about it now. So sometimes, which is an example that I have later, I printed, or instead of using a full 3D volume, I used a plane and surface and create a G-code off of that. And then I actually printed on top of something to give an interesting form. But so in that instance, I started the equivalent of 2 inches up, which you have to do the conversions on that to millimeters. But I wanted to print over something to create a cool form. And as that, use the object below as my form work. So I didn't want to start exactly at 0, 0, 0. So I actually started 2 inches above that, which is something you can change here. Then you want to have a thickness to it. So traditionally, for a pretty clean layer thickness of material, 0.15 millimeters is pretty typical for when you're 3D printing with the regular software, and I found that it works pretty well here. And then this count part, you just want to make sure that it's high enough to cover your whole volume so nothing gets left behind in the end. So, just to make sure, I always use a panel here to, make sure that all my series is getting counted correctly. So I want something at 0 and then 0.15 millimeters up the whole direction, which is what I'm getting here. All right, so after that, that's how we get our whole contour. Well, now that we have all the contours, we want to take those curves and divide them to get points, because we need the points to act as coordinates, and that's what our G-code is going to read. It won't read lines. The G-code makes its own lines by connecting points. So we need to get everything broken down into points. And that's what you can see over here. So you use the divide curve function, and you connect your contours to your curve. And then you want to break that up into as many points as you want. So when I talked earlier, the more points that you have on your geometry, the higher resolution it's going to be, so that it'll have a nicer finish. So I have 80 here, it's pretty aggressive, but I want a really high finish at the end. But if you want a lower finish, you could slide it down, and now you're only connecting 5 points along each side, which is significantly less. So it's going to go a little bit quicker, but it's also not going to have it won't have a near as quality finish, especially if you were doing a more complex geometry. But I'm going to go ahead and set that back to what it originally was at 80. So each ring is divided into 80. So this whole ring of the square is 80, this whole ring is 80, this whole ring is 80, and so on and so forth. So then from there, you just want to, check that you're getting the right points, which it looks like we are, because we're moving around the square in the first layer, so we want our y to be 0 because we want to start at 0 in the height. And yeah, it looks like we're getting those nice points. So then we want to move on. So now that we have these points, to make this G-code work a little bit more efficiently, we want to blow these points apart. So that's why I use the deconstruct. And then that'll break it up into the X component, Y component, and Z component, because we want to manipulate it later to make it a little bit more efficient for us. All right, so now that we have that, let's talk about um, how to how to add the extrude function into this. So in between each point, we want we need material to be extruded out, but we don't know exactly how much we want. So this is always a little bit of trial and error, but this is this is what I've done and it works for me. But again, it depends on how big your model is, about how much material you want to extrude. And this is, a nice variable that you can control later on, to experiment with things. So, um, so you take all your points. So you want to take some of them into that deconstruct function and the deconstruct function, but then you also want to take some, and then this is how we're going to work for the extrusion. So you take the points as well as the height, which is your layer height for Z, and you plug that into the list length. And then you again want to make a series. So your points come into the list length, and then you connect that into the count here. And then for the extrusion height, you take your Z height, which is called the step, and you bring that into the step here. So in this series now, we're beginning to get, or we're getting, the amount of material that's going to happen in each ring. So now we can begin to assemble our G-code itself. So so you want a format function, and then in a panel, you can type this out, G1 space F, and then in brackets 0. F will eventually be our speed, comma, X1 space, comma, Y2, Z3, E4, just exactly like this. This is what we want. This matches from the PowerPoint the function that we want, because this will be what will be read as G-code. So then moving to this F of 0 is our speed. And then at 0 here in this format bar, we have 1500 plugged in. Now, obviously, the speed can be variable for you. Again, something now that we've broken up our G-code, instead of relying on a software, this is something we can easily manipulate and create something a little bit cooler, or, a little something outside the norm of what you're originally expecting. Because, if we 3D print this is just a plain old box, but you can see how later on, how we can, create something different. So we'll get back to those pictures later, but, just setting up the G-code first. So create this on a slider, and then plug it in. So I want 1500, but again, something, if you want to go faster or slower for experimentation, by all means go ahead. So then we take our deconstructed points and we plug that in. So our X component matches up with the 1, our Y component matches up with the 2, and then our Z component matches up with the 3, just like we have here. And then we want to take those extrusion factors and plug them into the final spot. So again, everything that we have here is broken up so that it can be customizable any way that we want. We can, change the number of points that we have. Back here, we can change the number of points that we have. We can change the layer height. Now, you can only go so crazy with that, because if not, then the material will stop touching, and then it'll be a jumbled mess of spaghetti. But if that's your desired outcome, then by all means go ahead. So then finally, once you get the format, you'll get a text box, and that's where you plug in a panel. So then, as you can see here, this is what our original format that we wanted, and this is what our format's looking like now. Now, originally I had the F after the E in the slideshow. It's not a big deal to have it whichever way you want. I just did it this way. So, in your first point, it's going to tell your G-code's telling your machine to move at 1500 millimeters per minute. And it's telling it to move to these coordinates, which is the culmination of all the points that we've brought together in this formatting text. And it's telling it to extrude nothing because obviously we don't want it to extrude before it hits the first point. But then as soon as it hits the first point, we're telling it to extrude 0.15 millimeters of 0.15 millimeters of material, which we get going because you need material to come out each time. But if you want, you can come in and actually change things, and then so that if you delete some of these extrusions, then it won't have any materials, and then it might create cool gaps that you may want. So then, to get this G-code out, you just need to save it as a Word document. Or so you can copy and paste it into your notes. And then when you save the file, you need to save it as .gcode. And then I traditionally take it, or my machine that I personally uses a SIM card or SD card, and which I put into the machine. Now, also, when you do this, you can copy and paste into your text document. You also need to bring back all these M factors. So you can literally just copy and paste all of these right into at the beginning of your text document, and then this one right at the end of the text document, and then you want to save it all as G-code. So this G28 through G28, you save at the beginning of these coordinates here, and then you save the final one at the end to shut everything off, and then that's when you actually can be able to run on your machine. So then, it's not the exact box that I showed, but this begins to show, things that you can create when you begin to manipulate your G-code. So here, I just have a regular box on the outside, but then I manipulated the points on the front or on the top to get this wavy pattern. So I've actually taken and manipulated the G-code in such a way that the material doesn't touch, and it just creates this thin spaghetti over the top. And then just like I showed you earlier, where you can manipulate the number of points, this is that same model, even stretched further, so that, there's a lot of holes going on at the top here. But then I also did a model where I increased the number of points and resolution on the model so that the material actually begins to touch again and create, a solid. Again, these are just overhead views of it. And also with this box, something that I did different is I added a plane to the top that I extracted all the points from, and then I had the machine run over each. I had the machine run over the top really, really slow, which again is something that we can manipulate in the F function that I showed you in Grasshopper. And you can take that F function and bring the speed way down, but leave the extrusion the same, and it'll keep extruding a lot of material at a time. And that's how this wavy pattern actually takes form, is that I began with a lot of material that I just pumped into thin air, or that I just pumped into the box to fill it up, and then I began to seal it. But the way that I began to seal it, I didn't use as many points as I could have or should have, and I actually created, these gaps and holes that you can begin to see here. And then because I decrease the points, the gaps get bigger and the values get bigger. And then here, you can begin to actually see through the box. And that's something, all three of these models, because we've manipulated the G-code in such a way that, we originally just started with a plain old box, but we manipulated our own G-code that, this will never be replicated the same way again. This will never be replicated the same way again. We can use that same G-code that we produced and run the points through again, 3 different times, and then each time it'll be completely different from here just because of the randomness of, when we allowed the extruder to just hover over top and just, extrude a lot of material and not touch anything. So that, it's able to add a randomness to what you're doing, but a control randomness, because again, you're the one that created the points from the original figure. So then here, I also did this again, but I did it with a different material or medium, which was concrete. And here the exercise was playing with the extrusion. I kept the speed the same. So actually, I manipulated my G-code. So at certain points, it would, release a little bit of material, which you can see here, which are these really stringy, pieces. But then at certain points, I had it, extrude a whole lot of material, really quickly. And that's where you get these super huge blobs. And all of this, I controlled it enough to realize, that this was going to happen at the corners or at the edge. Because I knew exactly what I did with my G-code. So I could tell you I couldn't tell you exactly what final form it would take, but I knew these blobs would happen, at these corners, because I knew I'd programmed it, to extrude a lot of material at these points. Because all of this, is just a big game of connect the dots. This was actually an experiment that I did where I played with the extruder Z height. So the extruder went in a straight line, again, because I had mapped it over just a simple plane and extracted points from it, but I manipulated the Z height in those coordinate system so that it would go up and down. And what happened was that sometimes it got so close, because this was a pretend floor slab, so this mesh is kind of acting like rebar. So the extruder got so close to this, what would be mesh rebar, that it actually forced a lot of material through it and, created these cool little, little pillow looking things of clouds that I like to call them, of concrete that poked through the mesh. But then where I didn't let the Z get so close, it creates these super huge valleys. And again, I know where these valleys are going to happen, but because of the randomness of the material and, that I've created, that, the G code's always going to remain the same, but because of the randomness of the material, things like this, this ridge will happen again, but it's not going to be exactly the same. And then again, this was just, a simple cylinder, but then this was a point where I didn't start at 0, 0. So when I began printing it didn't start at the bed. It actually started a half an inch above the bed, so that everything had a moment to fall before it actually made contact with the bed. So then, as it started building up on top of each other, again, it created that randomness of, it had a free moment to fall before it actually made contact with itself again. And that, creates this cool spaghetti-ness. But, it actually begins to take on a pretty significant thickness that, maybe could be turned into a column and actually support weight. And then again, this was just a test of, the extrusion. So it started here, and then as it began connecting the points, I had the extrusion manipulated so that it would begin to create a gradient. So as it goes along, it begins to extrude more and more material until you finally get to this big blob at the end. Again, it's one of those things, you know what you programmed, but if you run it again, it's going to create a different outcome. So at the end of all this, you might be thinking, well, why? Well, one of my old professors who actually got me started in this research, he kind of does the same thing where he uses this process with concrete and plastic, and he's looking at creating structural elements that are both aesthetic and structural in purpose, but all come from 3D printing. So his column here in the upper corner is actually there is the extruder comes down. It's all vertical, but the extruder comes down and then actually smushes the concrete after it prints, and then lifts back up, creating this interaction between the rebar and the concrete, which actually begins to take on the fluting of traditional columns. So, it begins to be both, structural, but also an aesthetic application. Having the same thing here, kind of like we did, where he played with different points of just this original form that began to create the spaghetti and like coily effect. So why this is important, and like it's something cool to know, is that your form comes from the process. So it can be used as like a form finding mission, and the building doesn't actually just have to be the pristine copy of your original model. And then if you're doing something like building scale, like a panel, but you don't want them to be all the same, you want them to be customizable. Each iteration can be run multiple times. Each iteration can run multiple times and get you different effects, which will all be very similar, but then again, they will all be very different. So there's a lot of customization that can happen within this. So, like one of my professors did, he began to create interior structural components of buildings, like this column here. Or, just like I had mentioned, you can use it to create, things like acoustic or facade panels, because of hacking the knowledge and, knowing what to expect, but also the material and the process allows for something new to happen that you may not completely know about. All right, thanks. That's all.